right now, you're breathing, and you're not thinking about it at all. But something extraordinary is happening inside you while you do. That breath just crossed into your lungs, then into your bloodstream, and your heart is already pushing it through your whole body. Somewhere inside one of your cells, right now, there's a single molecule of oxygen. It doesn't know where it's going. It doesn't need to. Your body has done this automatically every second you've been alive. That oxygen is about to become part of a chain reaction inside your cells that releases energy. Energy your body uses to move, to think, to keep your heart beating, to simply keep you alive. Now go smaller, down past your cells, down to one single atom, a part of you right now. That atom has no memory, no thoughts, no idea that it's sitting inside a human being. But it has a history, and that history is much, much older than you are. Older than the cities you live near. Older, even, than the villages that came before those cities. Older than the small hunter-gatherer groups that once followed the seasons across this land. Go back further than humans altogether, and it's mammals, spreading across an emptier world. Earlier still, that same land belonged to the dinosaurs. And before the dinosaurs, the first animals were only just beginning to appear. Keep going, and Earth doesn't even look like Earth anymore. Just a bare, scorched world, waiting to become something else. Go back far enough, and Earth simply isn't there yet. Neither are any of the other planets. There's only a vast cloud of gas and dust, collapsing slowly under its own gravity. And even that cloud has a history. Its atoms were forged through the lives and deaths of stars. Stars took simple elements and turned them into the ingredients of planets. And eventually, into the ingredients of life. When those stars died, they scattered their newly made elements out into space, into clouds that would form new stars and new worlds. Somewhere inside one of those clouds, our own solar system would eventually be born. But even our galaxy, the Milky Way, wasn't the beginning either. Rewind further, past the stars, past even the galaxies, and there's just a formless haze of hydrogen and helium drifting through the dark. The universe was young, hot, and almost completely dark. So where did the first atoms come from? The first stars, space itself. Keep going back, and you reach a moment when the universe looked nothing like the one you know today. Search for Earth, and you won't find it. Look for the sun, and there's nothing there at all. So how do we get from there to you? Let's begin at the very birth of the universe. 13.8 billion years ago, none of the universe we recognize today existed in any familiar form. And here's the honest truth. We don't actually know what happened at the very first instant. Travel back far enough, and Earth disappears. Then the moon, then the sun. Then the entire Milky Way, taking every star and planet with it. Keep going, and even the periodic table disappears. No oxygen, no carbon, no iron, no water. All of it still billions of years away. The universe was too hot, too dense, and too energetic for atoms to exist in any form we'd recognize. Go smaller still. Inside an atom are protons and neutrons, and inside those even smaller particles called quarks. But at the earliest moments, we can actually describe, even that picture stops being useful. This wasn't a universe of stars and planets, or even atoms. It was an unimaginably hot, dense state, still deciding its own rules. And here's one of the biggest misconceptions about it. The Big Bang wasn't simply an explosion happening inside empty space. There was no pre-existing empty room for the universe to explode into. Space itself was expanding. Every region of the early universe was part of that same hot, dense state, and as space expanded, it cooled. Energy filled everything. Particles collided constantly. Matter and antimatter were created and destroyed over and over. But the universe kept expanding, and expansion changed everything. As it grew, its temperature kept falling. The very first moments were unbelievably fast, fractions of a second, so incredibly small, our sense of time barely applies. As it cooled, energy could finally form stable particles. Quarks, electrons, neutrinos, and photons. The raw ingredients that would eventually build atoms, stars, and planets. But there was a problem. The early universe produced matter, and its opposite twin, antimatter. And when they meet, they destroy each other. Almost everything could have vanished right there. But somehow, the universe ended up with a tiny excess of matter. For roughly every billion particles of antimatter, there was one extra particle of matter left over. That tiny imbalance changed everything. Because if matter and antimatter had cancelled out exactly, none of what came after would exist. Not the stars, not you. As the universe kept changing, quarks became bound together into protons and neutrons, the basic ingredients of atomic nuclei. But we're not ready for atoms yet. The universe is still far too hot for that. In just its earliest moments, the universe had already begun a transformation that would eventually lead to everything we know, and the story was only beginning. When people say the universe began, they don't mean something exploded into an empty space that was already there. Imagine instead drawing several dots on a stretchy sheet, each one a galaxy, and then stretching the sheet itself. Every dot sees every other dot moving away. And here's the strange part. No single dot is the center. They all look the same. That's because it's the space between them that's expanding. The universe isn't expanding into anything. The room itself is changing. Now run that backward. If space is expanding today, then in the past it was smaller, hotter, and far denser. Keep running the clock back, and you reach an early universe so hot and dense that atoms, molecules, and even stars couldn't exist yet. Instead, the universe was filled with radiation and elementary particles, interacting at enormous energies, in an environment nothing like the one we live in. Then something changes. Space expands, the universe grows larger, and the same energy spread over more space means the universe cools. And cooling matters enormously, because things that were impossible at higher temperatures suddenly become possible. The universe, at this point, was less than a single second old, not a minute, not a millisecond, a fraction of a second almost too small to describe. At these earliest moments, our physics reaches a boundary, a place where gravity and quantum mechanics would need to meet, and we don't have that theory yet. One idea says something extraordinary happened here, an incredibly brief, incredibly fast burst of expansion called cosmic inflation. We don't know every detail of what may have caused it, but it could explain several strange features we still observe in the universe today. Tiny quantum fluctuations may have been stretched to enormous scales, becoming, much later, the seeds that galaxies would eventually grow from. Whatever happened in those earliest moments, the universe kept expanding and cooling, and its first real ingredients began to appear. Quarks, electrons, neutrinos, photons. But the matter-antimatter problem returns. If the early universe had made exactly equal amounts of both, nearly everything could have annihilated into pure radiation. Instead, it ended up with a tiny excess of matter. And everything you're looking at right now exists because that matter survived. As the universe cooled further, quarks could no longer roam freely. They became bound into protons and neutrons, the future cores of atoms. In an almost unimaginably short time, the universe went from an extreme formless state to one containing the basic ingredients needed to build matter. Within the next few minutes, it would cool enough for protons and neutrons to combine into the very first atomic nuclei, mostly hydrogen and helium. But these aren't full atoms yet. Electrons are still roaming free, and the universe remains a hot, glowing plasma for hundreds of thousands of years to come. There are no stars yet, not a single one, and now the universe simply has to wait. To understand the universe's first second, forget something you've learned from everyday life. The universe isn't fundamentally made of tiny balls flying through empty space. At the deepest level, it's made of fields. What we call a particle is really just a ripple in one of those fields. A disturbance that behaves like a particle when we look at it. At these temperatures, those fields were carrying enormous amounts of energy. Energy about to become the raw ingredients of matter. The early universe was, in effect, a gigantic particle factory, constantly turning matter into radiation, and radiation back into matter, everywhere, all at once. Among the most important particles were quarks, fundamental, not made of anything smaller, which would eventually become part of protons and neutrons. Quarks have a strange property. They don't like existing alone. A force called the strong interaction binds them together. And unlike gravity, that force gets stronger the harder you try to pull quarks apart. Pull hard enough, and the energy creates new quarks instead. There's another family of particles too, called leptons, including the electron and the neutrino. Neutrinos interact so weakly that enormous numbers of them are passing through you, right now, as you watch this. 4 fundamental forces run the entire show: electromagnetism, the strong interaction, the weak interaction, and gravity. Together, they decide everything that happens next. And now we reach one of the greatest mysteries in this whole story. Why is there something, instead of nothing at all? If the early universe had produced perfectly equal amounts of matter and antimatter, almost all of it could have annihilated into radiation. Not a single star would exist to ever light the darkness. No planet or chemistry or even life itself. Nobody left to even ask why. But the universe wasn't perfectly symmetrical. Somehow, a tiny excess of matter survived, roughly one extra particle for every billion that were destroyed. We call that imbalance matter antimatter asymmetry. We know it happened. We still don't know exactly why. That tiny leftover became the entire material the visible universe would eventually be built from. As the universe kept cooling, quarks became confined inside protons and neutrons. No longer a free-floating soup, but real building blocks for atomic nuclei. Within minutes, those protons and neutrons began joining together, forming the first atomic nuclei, mostly hydrogen, a good amount of helium, barely anything else. Less than a few minutes into the entire history of the universe, it had already gone from formless energy to holding its very first elements. We now have the ingredient, the four forces, hydrogen and helium, and now, the universe waits, 3 minutes, 1 hour, 1 day, 1 year. The universe is born bright, then quickly becomes a hot, opaque fog. Light exists, but it can't actually travel. The universe is now a few minutes old, and its very first atomic nuclei have already formed, mostly hydrogen and helium. But there's a problem. The universe is still packed with free electrons, and electrons are extremely good at scattering light. So even though the universe is glowing, filled with photons, none of that light can travel very far. It's opaque. Imagine standing inside a thick fog with a flashlight. The light is there. You know it's there. You just can't see through it. That's roughly what the early universe was like, full of light, but with no way for that light to travel in a straight line. But the universe doesn't stop. Space keeps expanding, and expansion means cooling. The universe grows less energetic, less dense, less violent. And eventually, something that was impossible before becomes possible. Electrons can finally stay bound to atomic nuclei. Around 380,000 years after the beginning, the universe has cooled enough for that to happen. A proton captures an electron, and you get hydrogen. This moment is called recombination, though these are actually the very first neutral atoms, not old bonds being remade. And this changes everything. With so few free electrons left to scatter it, light can finally travel, not for a few meters, but across the entire universe. The cosmic fog lifts. For the first time, the universe becomes transparent. Some of those exact photons have been traveling ever since. Nearly 13.8 billion years, stretched by the universe's own expansion into microwaves. We call it the cosmic microwave background. The oldest light we can observe directly, a photograph of the universe at 380,000 years old. And the most important detail in that photograph isn't how smooth it looks. It's the tiny imperfections, regions just slightly denser than others. Gravity noticed those differences. Over enormous stretches of time, it would amplify them into something far larger. The slightly denser regions pulled in more matter. More matter meant stronger gravity, and stronger gravity pulled in even more matter. Those tiny fluctuations would eventually become the seeds of every galaxy that would ever exist. But right now, something strange has happened. The universe is transparent, light can travel freely. And yet there's almost nothing out there to see. Not a single star burns anywhere. Whole galaxies are still nowhere close to existing. The universe has become transparent, and now it becomes dark. This period is known as the Cosmic Dark Age. There are almost no sources of light anywhere. Not a single star burns. Imagine opening your eyes somewhere inside this universe. The sun hasn't ignited. The Milky Way doesn't exist. Mostly there's just hydrogen and helium. But the universe isn't perfectly smooth. Some regions hold slightly more matter than others, and gravity doesn't care how small that difference is. A little more matter means a little more gravity. That extra gravity pulls in more matter, which makes the gravity stronger still. A feedback loop. Over enormous stretches of time, matter stops being evenly spread out. It gathers into clumps, and those clumps pull in still more. Eventually, a vast structure begins to emerge. Dense regions connected by enormous filaments, separated by huge, nearly empty cosmic voids. Much of the gravity doing this work doesn't come from ordinary matter at all. It comes from something we call dark matter. We've never directly detected a dark matter particle. but we can clearly see the gravitational effects it produces. Invisible scaffolding, with ordinary matter following behind. Small structures form first. Then some of them merge, building larger gravitational systems. Enormous invisible wells that hydrogen gas starts falling into. Imagine one of these gas clouds. There's no star inside it yet. But gravity keeps pulling the gas inward, and compressed gas heats up. The cloud may begin rotating. Matter keeps falling toward its center. And eventually, the temperature and pressure there will become extraordinary. Gravity is slow. It doesn't build a galaxy in a second, or a star in a minute. It can take hundreds of millions of years. But the universe has something humans don't. An enormous amount of time, and it's been using every second of it. For hundreds of millions of years, gravity has been pulling, compressing, heating, building, quietly, in total darkness. And now, something is about to happen that will change the universe forever. Then, inside one enormous cloud of hydrogen, gravity does something extraordinary. It squeezes the gas tighter and tighter and tighter, until the center becomes hot enough for something entirely new to begin: nuclear fusion. The very first star in the universe is born. Don't picture a star as a giant ball of burning gas, the way wood burns. Deep inside, something far more powerful is happening. Hydrogen nuclei are forced together under enormous pressure and heat, eventually combining into helium. And a tiny bit of mass converts directly into energy. That energy is what makes a star shine, and it creates a kind of cosmic balance. Gravity pulling inward, fusion pushing back out. As long as those two forces stay balanced, the star survives. The first stars, though, were probably nothing like our Sun. With almost no heavy elements around yet, the first stars could grow enormous. Some many dozens, even hundreds, of times the mass of our Sun. And there's a strange rule in stellar life. The more massive a star is, the faster it burns through its fuel. Our Sun can shine for billions of years, but a truly massive star might live only a few million, almost nothing, on a cosmic clock. The first stars were spectacular, and they were temporary, but hydrogen was only the beginning of what they could build. Inside a massive star, fusion doesn't stop at helium. It keeps going, building carbon, then oxygen, neon, magnesium, silicon, layer after layer, like a cosmic onion. Eventually, the most massive stars build a core dominated by iron. And iron is different. Fusing it further doesn't release energy anymore. It costs energy. The star has hit a wall it can't push past. And gravity, which it had been holding off its entire life, finally wins. The core collapses in an instant. The outer layers get blasted back out into space. We call this a supernova, one of the most violent events in the universe. And this is exactly why the first stars matter so much. Their deaths scattered brand new elements across space that the early universe never had on its own. The universe had been almost entirely hydrogen and helium. Now it had carbon, oxygen, silicon, iron, the beginning of real chemistry. Rocky planets need exactly these kinds of elements: silicon, oxygen, iron, magnesium, carbon, the future ingredients of minerals, rocks, oceans, and eventually, living things. None of that exists yet. The universe is still only just gathering the ingredients. But remember where we began? With you. The carbon in your body, the oxygen you breathe, the calcium in your bones, the iron in your blood. None of it was created when Earth formed. None of it was created when you were born. Its story began here, inside dying stars. The first stars illuminated the darkness, built new elements, and then scattered them across space when they died, leaving the universe holding something it never had before. The ingredients for rocky worlds, for complex chemistry, and eventually for life. Stars don't stay isolated forever. Gravity has been working on something much bigger, gathering stars, gas, dust, and dark matter into enormous structures. These early systems weren't beautiful spiral galaxies like the one we live in. They were messy, irregular, and constantly changing. We call them protogalaxies. And galaxies don't always grow quietly. Sometimes they collide, gravity pulling them together, bending their paths, flinging their stars into new orbits. Here's the surprising part, though. When galaxies collide, their stars almost never actually crash into each other. Even with billions of stars inside a single galaxy, the distances between them are so enormous that a collision is more like two ecosystems passing through one another. And galaxies aren't scattered randomly. They form preferentially along the enormous filaments and dense regions of that cosmic web gravity built earlier. Over billions of years, the web filled with galaxies. hundreds of billions of them spread across the observable universe. Gravity doesn't build every galaxy the same way. Some stay irregular. Some become smooth, ancient elliptical galaxies. Others develop elegant spiral disks. A galaxy holds huge clouds of gas and dust, and often a supermassive black hole at its center. Gas collapses into new stars. Those stars live and die, returning their material to the galaxy, which becomes part of the next generation. A galaxy recycles itself. And somewhere inside this enormous, expanding universe, something familiar is finally beginning to take shape. Our own galaxy, the Milky Way. It didn't appear fully formed. Smaller structures merged together, gas accumulated, new stars were born, and gradually, a much larger galactic system emerged. But don't look for Earth yet. The sun hasn't been lit. The solar system is still nothing more than an empty patch of space. Even the specific cloud of gas that will eventually become our sun hasn't formed yet. We're still billions of years away. But something important has changed. The universe now contains galaxies. Galaxies contain stars, and those stars keep creating and recycling heavier elements. Those elements are now mixed into the raw material future stars and future planets will eventually be built from. Somewhere inside this galaxy, a cloud of gas and dust will one day collapse and become a star. And around that star, something extraordinary is about to happen. Planets will begin to form. This is the Milky Way. From Earth, it looks like a faint band of light across the night sky. But from outside, it's almost impossible to comprehend. It's a structure roughly 100,000 light-years across, holding an enormous number of stars, likely hundreds of billions of them. Every single point of light you'd see is another star. Some larger than our sun, some smaller, some ancient, some newly born, many with planets of their own. We're not at the center of the galaxy, and not near the edge either. Somewhere in between, in a smaller structure called the Orion Arm. Our solar system sits roughly 26,000 light-years from the galaxy's center. A relatively quiet neighborhood, in galactic terms. The Milky Way didn't appear fully formed either. Like almost everything else, it was assembled over billions of years, through countless mergers. Some of those mergers were violent. A smaller galaxy could pass too close, and gravity would simply tear it apart, its stars absorbed into our own. Which means some of the stars orbiting inside the Milky Way right now may have been born somewhere else entirely. Ancient immigrants from galaxies that no longer exist. When smaller galaxies get torn apart, their stars leave behind long trails, still visible today. In a sense, the Milky Way carries its own fossils. At the very heart of our galaxy sits a supermassive black hole called Sagittarius A star, about 4 million times the mass of our sun. But we're tens of thousands of light-years away from it. It doesn't control the galaxy, like some kind of cosmic vacuum cleaner. The Milky Way behaves like an ecosystem. Gas flows through it, and stars are born, age, and explode, constantly recycling their material. And somewhere inside this enormous galaxy, something very ordinary is happening. A cloud of gas and dust, drifting quietly through space. It already contains hydrogen, helium, carbon, oxygen, silicon, and iron. Elements created by generations of stars that lived and died before it. The ingredients for an entire planetary system are already sitting right there. But the cloud isn't a planet yet. It isn't even a star. Not yet. Think about the scale of what's about to happen. The Milky Way holds hundreds of billions of stars, and our future solar system begins in one tiny corner of it. There's nothing special about this particular location. No cosmic significance, no purpose behind the choice. Just one ordinary region in one ordinary galaxy. And yet, this ordinary cloud is about to become the center of our entire story. We've finally reached the neighborhood where our own story begins. This isn't a cloud like the ones drifting across Earth's sky. It's a vast region of cold gas and dust. Mostly hydrogen, some helium, and scattered throughout it, tiny grains of material recycled from the remains of older stars. For a long time, this cloud stays relatively stable, until one region becomes dense enough for gravity to finally take over. Once gravity starts winning, material begins falling inward. More material arrives, the region grows denser, and a tiny imbalance becomes a full gravitational collapse. The cloud already has some rotation, and as it collapses, that rotation speeds up. The same reason a spinning skater speeds up when they pull their arms in. That spin means the material doesn't just fall straight into the center. It spreads out into a rotating disk, with most of the mass gathering densely in the middle. At the center of that collapsing cloud, something is becoming enormous. A protostar, heating up as material keeps falling into it. Eventually, the temperature and pressure become extreme enough for hydrogen nuclei to begin fusing. A star has been born, our Sun. But the Sun wasn't born alone. Around it was an enormous disk of gas, dust, rock, and ice, and every planet, including Earth, will come from it. At first, the future planets don't look anything like planets, just microscopic grains of dust, colliding, and sometimes sticking together. Grain by grain, dust becomes pebbles. Pebbles become larger bodies. But this process is anything but gentle. The young solar system is chaotic. Objects smash into each other constantly. Some break apart. Some merge. Some get thrown into entirely new orbits. Eventually, some objects grow large enough for their own gravity to matter. We call these planetesimals, the real building blocks of planets. And now gravity helps again. Bigger objects attract more material, which makes them even better at attracting still more. Over millions of years, some of these bodies grow into full planetary embryos. Rocky material dominating close to the Sun, different materials surviving farther out. The basic architecture of our entire solar system begins taking shape, right here, out of nothing more than leftover stellar debris. So why didn't all that material just become one giant planet? Because the disk around the young Sun wasn't the same everywhere. Close to the Sun, temperatures were extremely high. Many substances that could freeze into ice farther out simply couldn't survive here as solids. Farther from the Sun, temperatures dropped, and eventually conditions turned cold enough for water and other compounds to freeze solid. That temperature difference decided what kind of planets could form where. Close in, rock and metal dominated, stuck, and gravity took over. Eventually, several rocky worlds emerged. Mercury, Venus, Earth, and Mars, small, dense, and metallic, compared to what was forming farther out. Out there, with far more solid material available, planetary cores could grow massive enough for their gravity to capture huge envelopes of hydrogen and helium. Jupiter grew into an actual giant. Saturn followed. Farther out still, Uranus and Neptune emerged, reshaping the entire architecture of the solar system around them. Not everything became a planet, though. Between Mars and Jupiter, enormous amounts of leftover rocky material remained. The asteroid belt. Farther out, the leftovers were different, icy bodies, cold enough to survive. That became the ancestors of comets. When a comet falls close to the Sun, sunlight heats its surface, releasing gas and dust, and giving it that spectacular tail. Here's another secret. The planets weren't necessarily born exactly where we see them today. Gravity let them migrate, some inward, some outward, over time. The solar system's final layout wasn't simply drawn at birth. It was negotiated by gravity, one interaction at a time. Jupiter, being so massive, became one of the great gravitational architects of our solar system, scattering smaller bodies wherever it pleased. Meanwhile, the inner solar system was becoming a battlefield. Dozens of growing worlds colliding, merging, breaking apart, changing orbit again and again. Every collision changed the future. A world could grow larger, lose material, get thrown into the Sun, or get ejected into space entirely. The planets we know today are simply the survivors of this enormous, violent cosmic competition. And somewhere among all those violent collisions, one particular planetary embryo kept growing, gathering rock, metal, and countless smaller bodies with every impact. This is Earth becoming larger. But it's nowhere close to the blue planet we know. Its interior intensely hot, its surface constantly bombarded. And Earth still has some of its most violent moments still ahead of it. A large planetary body is about to collide with the young Earth, vaporizing rock and throwing mountains of debris into orbit. From that debris, something entirely new will eventually emerge, the Moon, and the collision that creates it will reshape Earth forever. After millions of years of collisions, migrations, and scattering, the chaotic construction phase finally begins to calm. A star at the center, rocky planets close to it, giant worlds farther out, asteroids and comets scattered between and beyond them. And among all of these worlds, one small planet is about to become extraordinary. But first, it has to survive. This is Earth, the planet we know, covered in oceans, wrapped in atmosphere, filled with life. But go back far enough and Earth was hell. The young Earth was still growing, with rocks and planetary bodies constantly crashing into it. Every collision delivering energy, and energy means heat. The more Earth grew, the more violently it was heated, by collisions, by radioactive decay, and by the sheer pressure of its own gravity. Enough heat accumulated to melt enormous portions of the planet. In some models, the surface may have been covered by a global ocean of magma. Imagine standing there. There's nowhere to stand. Nothing resembling an ocean, or soil, or a single living thing, anywhere. But even while heat was tearing the surface apart, another process was quietly building Earth's internal structure. Heavy elements like iron sank toward the center, while lighter rock stayed above. Earth was separating into a metallic core, a rocky mantle, and a crust. Earth's surface, meanwhile, was nothing like the world we know. No oxygen-rich air. Volcanoes released water vapor, carbon dioxide, and nitrogen, gases you couldn't have breathed. The blue sky we take for granted didn't exist yet, in any form. Earth's atmosphere would keep evolving right alongside the planet itself. Earth wasn't isolated either. It moved through a young solar system still full of unfinished worlds, and asteroids that kept on striking. And eventually, one encounter would change Earth forever. A large planetary body, often called Theia, collided with the young Earth. We don't know exactly what that object looked like, but this giant impact collision remains the leading explanation for how the Moon formed. At planetary scale, this wasn't an explosion like a bomb. It was a genuine collision between two worlds. Rock melted. Some of it vaporized entirely. Enormous quantities of debris were thrown into orbit around Earth, and for a while, Earth was surrounded by its own ring of wreckage. Rock fragments collided with each other, some breaking apart, others merging into larger bodies. Gravity doing what it always does, gathering matter back together. Slowly, that debris assembled into something new. The Moon formed not in a single instant, but through repeated collision and accretion. From this point forward, Earth was no longer alone. It had a companion, and it would have won for the rest of its history. The Moon didn't start out where we see it today, either. It was much closer, and from Earth's surface, it would have looked enormous. Over billions of years, it has slowly drifted farther away. Today, sitting roughly 384,000 kilometers out on average. The Moon-forming impact helped establish the gravitational relationship that would later shape Earth's rotation and its tides. High tide, low tide, again and again, one of the great rhythms of Earth's future, set in motion by a collision billions of years ago. But the Earth of this exact moment is still almost completely hostile to anything alive. Soon, though, it will get its oceans. The collision is over, the young Moon is forming, and Earth is still burning. But now, finally, something begins to change. Earth starts losing heat. There's only one direction that heat can go: outward. Earth radiates energy into space, and the planet slowly cools. Molten rock begins forming a solid exterior. A world that was almost entirely hostile, molten terrain is finally beginning to acquire real surface. That first crust isn't stable, though. It's thin, hot, and constantly broken. Volcanoes keep punching through, adding fresh rock, which cools and breaks again. The young Earth stays extraordinarily active. Volcanoes become one of the planet's great engines, releasing gases straight from Earth's interior. Water vapor, carbon dioxide, nitrogen, sulfur-bearing gases. Over geological time, this volcanic activity helps shape Earth's very first atmosphere. It's still nothing like the air you're breathing right now, though. There's no oxygen-rich atmosphere yet. That's still billions of years away. One of the most important ingredients is already here, though. Water, likely present in Earth's original building material from the very start. As Earth kept cooling, something extraordinary became possible. Water vapor could finally begin condensing into liquid. And then, for the first time, rain. Imagine the first time liquid water ever fell from the sky onto young Earth. The surface was still hot, it evaporated, and rain fell again. And again. Water collected in the lowest places. Pools became lakes. Lakes connected. And eventually, enormous bodies of liquid water covered parts of the planet. Earth was becoming a water world. The same planet once covered in molten rock now carried liquid water across its surface. And oceans don't just sit there. They start changing the planet. Water reacts with minerals, dissolves chemicals, and carries them across enormous distances. Deep beneath the ocean, volcanic activity creates hydrothermal systems, pumping chemically rich, hot fluids straight through Earth's crust. The planet was becoming a gigantic chemical laboratory: liquid water, an atmosphere, volcanic energy, minerals, chemical gradients, and enormous amounts of time. For billions of years, stars had been making elements. The solar system had assembled worlds from them. And now, finally, the ingredients were all together. Most people never trace their own body back this far. Most never even think to. This channel exists for exactly that, following an ordinary thing back to where it actually began. If this is making you see something ordinary differently, that's the whole point. Hit like, subscribe, and the next thing we take apart like this will find you. Earth had oceans and atmosphere, volcanoes, minerals, energy, and enormous amounts of time. But there was still something missing entirely: life. And this may be the greatest mystery in this entire story. How do you turn a planet full of chemicals into a planet full of living things? We don't know exactly. And that's actually important. This part of the story is still genuinely being written by scientists working right now. To even begin, you have to stop thinking like a biologist and start thinking like a chemist. Before there were cells, there were only molecules. Molecules collided constantly. Some reactions produced new molecules. Some of those were more stable than others, and simply accumulated over time. The young Earth was an enormous chemical laboratory, and chemistry had billions of years and billions of opportunities to try different combinations. The ingredients life actually needed weren't exotic at all. Carbon, hydrogen, oxygen, all already present, reacting across oceans, rocks, and volcanic systems. In 1953, scientists Stanley Miller and Harold Urey simulated conditions thought to resemble the early Earth, inside a sealed jar in a lab. After running the experiment, they found organic compounds, including amino acids. It didn't create life, but it proved chemistry alone could build life's raw ingredients. Except an amino acid isn't alive. Neither is a sugar, or even a genuinely complicated molecule, just sitting there by itself. Life needs something much harder to build. A system capable of maintaining itself, using energy, and eventually, making copies of itself. One idea points deep beneath the ancient ocean, to hydrothermal vents. Chemical gradients rich enough to power early chemistry. Another idea points to the surface instead. Shallow pools that repeatedly dry out and refill, concentrating diluted chemicals together, cycle after cycle. Here's the frustrating part. We simply don't know which environment was life's actual birthplace. It may not have even been one single place at all. It might have been a long chain of chemistry, spread across several different environments, each contributing a different piece of the puzzle. But even organic molecules aren't life. Life needs information, chemical reactions it can sustain, and, above everything else, a way to reproduce. Imagine a molecule capable of helping build another molecule just like itself. Chemistry has acquired something extraordinary: copying. Copying alone isn't enough, though. Copies can contain errors. Some variants turn out more stable and reproduce more effectively than others. One especially influential idea, the RNA world hypothesis, suggests an early molecule may have carried information and driven reactions at the same time. But RNA is chemically complicated, and explaining how large amounts of it could have formed on the early Earth remains a real, unresolved challenge. Another problem: useful molecules need somewhere to actually work together. Floating freely in an entire ocean, useful reactions simply get diluted away. But certain lipids naturally organize into membranes in water, under the right conditions, forming tiny compartments that could concentrate chemistry inside a boundary. These wouldn't be modern cells. But imagine primitive compartments growing more complex, more stable, and occasionally dividing. Now suppose two of these primitive systems can reproduce, one slightly faster, one more stable. Over generations, those differences accumulate. Systems that reproduce more successfully simply become more common. Because once you have variation and inheritance, natural selection can begin. Somewhere along this enormous chemical journey, systems became more sophisticated, compartments more stable, information more reliably copied. Eventually, the first primitive cells emerged. Exactly what they looked like, or where, or the precise chain of steps. All of that is still unknown. But the story had crossed a genuine boundary. For billions of years, the universe had stars, planets, oceans, and chemistry. Now, matter could reproduce. And because copies can differ, and those differences can be inherited, life could finally start to evolve. The universe had entered a completely new phase. The first life probably wasn't spectacular. Strip away everything you'd expect from something alive. Eyes, a brain, even a skeleton. It was microscopic. A tiny package of chemistry, capable of maintaining itself, and making more of itself, about to become one of the most powerful forces on Earth. Once life existed, it had reproduction on its side, and every generation created new opportunities for variation, and survival in new environments. Some organisms lived where volcanic chemistry provided energy. Others occupied shallow waters. Life began spreading through almost every environment it could survive in. Then life discovered something extraordinary. Instead of depending entirely on chemical energy nearby, certain organisms evolved a way to capture sunlight directly. Photosynthesis. Among the most important were cyanobacteria, ancient photosynthetic microbes that used sunlight, water, and carbon dioxide to build their own organic matter. And there was a byproduct nobody was expecting to matter much yet: oxygen. At first, it mostly reacted with minerals and simply disappeared. In shallow seas, microbial communities formed dense mats, trapping sediment, growing upward, leaving behind layered structures we call stromatolites. Because these organisms were microscopic, they left no bones. Just chemistry, structure, and traces preserved in some of the oldest rocks on Earth. Then something strange happens to our story. For hundreds of millions of years, almost nothing seems to happen. Life stays overwhelmingly microscopic. If you stood on Earth during much of this time, you'd see an ocean, some rocks, volcanoes, and microbial mats. Nothing more. But nothing happened would be completely wrong. Life was quietly transforming the entire planet, producing oxygen year after year for millions of years. That oxygen was slowly accumulating in the oceans, and eventually, the atmosphere, setting up one of the greatest transformations Earth would ever experience. The gas that lets you breathe right now was, to many of Earth's earliest inhabitants, close to poison. Today, oxygen is everywhere, and every breath you take depends on it. But billions of years ago, it was almost a foreign substance on this planet. Certain ancient microbes had developed the ability to capture sunlight and split water, and oxygen came out the other side, as a simple byproduct. At first, almost all of it got consumed instantly by the surrounding environment. But the microbes kept working: sunlight, photosynthesis, oxygen, again and again. One of the biggest chemical sponges was dissolved iron in the oceans. Oxygen reacted with it, and the rusted results settled into sediment layers we still read today. Think about what rust actually is: familiar oxidation on a small scale. Now imagine an entire ocean's worth of iron rusting slowly over millions of years. For a long time, Earth's oceans absorbed almost all the oxygen being produced. But eventually, the balance began to shift, and oxygen started to accumulate. This is called the Great Oxidation Event, beginning roughly 2.4 billion years ago. Earth's atmosphere had crossed an important, irreversible threshold. And here's the twist. Oxygen, so essential to us, was genuinely dangerous to organisms adapted to a world where it had barely existed before. Some organisms died outright. Some retreated into oxygen-free environments that still exist today. Others slowly evolved ways to tolerate, or even use, the new gas. Some scientists call this transition the oxygen catastrophe, not one explosion, but a long, disruptive reorganization of Earth's entire chemistry. But oxygen had another property too. Under the right biochemistry, it could unlock far more energy than older, oxygen-free chemistry ever could. And that extra energy would eventually matter enormously, because complex life is expensive. Bigger cells, bigger bodies, all of it needs far more energy to run. Oxygen chemistry, high in the atmosphere, also helped create the ozone layer, which absorbs much of the sun's harmful ultraviolet radiation. That layer would later help make Earth's surface a genuinely safer place for life to expand into. Another accidental gift from microscopic organisms. Nobody built a factory. Nobody drew up a plan. Just billions of tiny organisms using sunlight, quietly changing an entire planet's chemistry as a side effect. Billions of years later, you take a breath. That oxygen reaches your cells and powers the chemistry that keeps you alive right now. It began with organisms so small you'd need a microscope to see them, and their innovation is part of the reason you can exist at all. For billions of years, life stayed mostly simple, single cells, tiny, efficient, constantly reproducing. Then something extraordinary happened. One primitive cell engulfed a bacterium. Normally, that's the end of the story for the bacterium. But this time, the bacterium survived. And something even stranger happened. The bacterium began providing something useful to its host, and the host provided protection and nutrients in return. Neither organism had to live entirely alone anymore. They'd become partners, a relationship scientists call endosymbiosis, one organism living permanently inside another. Over many generations, That relationship became more integrated, and what was once a free-living bacterium became something new. A mitochondrion. Every time your own cells use energy right now, you're benefiting from a partnership struck between two separate microbes billions of years ago. We know this happened because mitochondria still carry their own DNA, have a double membrane, and machinery that still closely resembles bacteria. Evolution hadn't built a new machine from scratch, it had combined two existing living systems into something neither ancestor was, by itself. The eukaryotic cell. These cells were extraordinarily different from simple bacteria. Internal compartments, a nucleus protecting their genetic material, and mitochondria generating usable energy inside. A cell had stopped being a simple room, and started behaving more like an organized, functioning little city. Later, a similar partnership happened again, this time with a photosynthetic bacterium, which instead of being digested, became something new, a chloroplast. Chloroplasts are what let plants and algae capture sunlight directly. And just like mitochondria, they still carry their own DNA. Once again, evolution had built genuine complexity, not from scratch, but through partnership between organisms that already existed. With all this new internal organization, cells could process energy more efficiently and interact with their environment in increasingly sophisticated ways. And eventually, some of them began doing something even more interesting, staying attached to each other after dividing instead of drifting apart. One cell could specialize in one task, another in a different one. Instead of every cell doing everything, different cells could divide up the work. This is the beginning of one of life's greatest experiments, multicellularity, thousands of cooperating cells behaving as a single organism. It came with a real cost, though. A cell that joins a larger organism gives up independence, and sometimes sacrifices itself for the whole. Cooperation had become more valuable than individual survival, a trade evolution would keep making, again and again, from here on. For billions of years, Earth's oceans had belonged to microscopic life. Then, in a relatively short window on the geological clock, that changed completely. Animals began interacting with each other in far more complicated ways. Some hunted, some hid, some developed armor, some burrowed into the seafloor. The ocean was becoming a genuine ecosystem, and that changed the rules of evolution entirely. Being eaten mattered now, just as much as finding food. Suddenly, being faster mattered. Being harder to eat mattered. Seeing danger before it arrived mattered. Evolution had entered a full arms race. One of the most important developments was the evolution of increasingly sophisticated ways to sense the world, starting with simple light-sensitive cells. Even the crudest ability to detect light told an animal something useful. Something is there. Over time, that ability grew into genuinely complex eyes. Seeing could now mean finding food or avoiding death. The ability to detect light had quietly become a weapon. Among the most iconic animals of this ancient ocean were the trilobites, armored, segmented arthropods, many with sophisticated compound eyes. They'd go on to become one of the great long-term success stories of these ancient Paleozoic oceans. Not everything here was small, though. Among the largest predators were radiodonts like Anomalocaris, large eyes, grasping limbs, built for active hunting. The Cambrian Ocean had become a genuine network of hunters, prey competitors, and survivors. And once predators became effective, defense became valuable too. Hard shells, sharp spines burrowing into sediment, or simply becoming faster. The evolutionary arms race was actively reshaping animal bodies, in real time, all across the seafloor. For the first time in Earth's history, the planet was starting to genuinely look like a world of animals. Scientists call this rapid diversification the Cambrian Explosion, though the name can mislead. It unfolded over millions of years, not overnight. But compared with the immense stretches of earlier Earth history, this burst of new body types and new ways of surviving was remarkably fast. There probably isn't one single answer for why it happened so quickly. Rising oxygen may have helped support bigger, more active animals. Predator-prey pressure pushed evolution hard in every direction at once, while changes in animal development may have opened entirely new possibilities. The Cambrian world wasn't one simple cause and effect. It was a feedback loop, with each new innovation creating pressure for the next one. And somewhere inside this explosion of animal diversity, another lineage was quietly beginning its own story. Early chordates, distant relatives of vertebrates. Their bodies already held structures that would eventually become central to us. A flexible internal support, and a nervous system running the length of the body. Fish eventually, and eventually us. Not yet though. Not for a very long time still. Think about how far this story has already come. Once, Earth was purely microbial. Now, animals are hunting, hiding, swimming, competing. The planet had become an ecosystem. But this was only the very beginning. Species would disappear, continents would move, new predators would emerge. And eventually, life was about to attempt something it had never once tried before. For most of Earth's history, life had belonged entirely to the ocean. The first cells, the first ecosystems, the first animals, all of it. But just beyond the waves was another world, almost completely empty of life. Leaving the ocean sounds simple. It was anything but. For an aquatic organism, land is an environmental nightmare. Water evaporates, your body has to support its own weight, and your food supply may not exist yet. To survive on land, life needed an entirely new toolkit. The first pioneers weren't giant trees. They were small and dependent on constant moisture. Microbial communities and simple algae-like organisms first established a foothold outside the ocean. Later, actual land plants began colonizing these bare, terrestrial environments. Nothing here resembled a modern forest. Just small plants, slowly occupying the edges of a previously barren, lifeless world. On land, water runs away instead of surrounding every cell like it does in the ocean. It has to be captured and protected from evaporation. Plants gradually evolved structures that made land increasingly livable, and once established, they began actively changing the land itself. They didn't do it alone, either. Fungi were already present, and their thread-like networks could exchange resources directly with plant tissue. These partnerships helped transform bare, mineral surfaces into genuinely productive ecosystems, trapping sediment and slowly building real soil. Once plants and fungi had established themselves, animals followed. Arthropods, with segmented bodies and jointed limbs, were among the very first to arrive. They could crawl across surfaces, hide beneath debris, and exploit resources the open ocean never offered. The land was no longer empty. Once there was food, there could be herbivores. Once there were herbivores, there could be predators. A terrestrial ecosystem was finally emerging. Meanwhile, in the water, certain fish, living in shallow, oxygen-variable environments, had fins built on unusually robust internal bones. Not legs yet, but raw evolutionary material that could eventually be modified into something completely different. This transition wasn't one sudden mutation. It unfolded across countless generations as descendants developed stronger internal supports and changed joints and digits. One of the most famous fossils in this whole story is Tiktaalik, discovered in 2004 in the Canadian Arctic, roughly 375 million years old. It still looked like a fish, but its skeleton held strong front fin bones capable of supporting weight, and a mobile neck, something fish don't have. Even the earliest tetrapods weren't simply fish that decided to walk onto land. Many still depended heavily on water and remained strong swimmers. Evolution wasn't moving in a straight line toward anything. It was branching in dozens of directions. Some lineages disappeared, others grew comfortable on land. Amphibian-like tetrapods became important early inhabitants of land, but reproduction remained tightly tied to water for most of them, still. Then evolution found a solution. The amniotic egg, which builds its own protected, water-filled world around the developing embryo. No pond required, ever again. Now vertebrates could spread across genuinely dry landscapes. Reproduction itself had finally adapted to a life fully lived on land. Think about what had just happened. A world that was once almost completely barren now had plants, fungi, arthropods, and land-reproducing vertebrates. Life had taken the environment where it began and expanded far beyond it. The planet now held two entirely separate worlds of life. But the land was about to become much, much stranger. Because once life learned to live there, the only question left was, how big could it get? The land had finally become alive. Then it became green, though nothing like the forest you'd recognize today. Welcome to the Carboniferous. If you walked into one of these ancient forests, you'd recognize almost nothing. No flowering plants, no grasslands, none of the trees you know. Instead, these forests were dominated by enormous relatives of today's club mosses and horsetails, growing to astonishing heights in wet, lowland environments. The atmosphere was different too. Oxygen levels ran substantially higher than today, with real consequences for anything that breathed. And that's when the forests started getting genuinely strange. Some arthropods reached sizes that look almost unbelievable now. Dragonfly-like griffinflies had wingspans measured in tens of centimeters. Millipede relatives like Arthropleura could grow past 2 meters long. Imagine walking through that forest and seeing one of those. Fortunately, you weren't there. Arthropods weren't the only ones thriving, though. The wetlands were full of amphibian lineages too, many still tied closely to water. But another group was quietly changing the rules. The early amniotes, whose ancestors had already evolved that protected, self-contained egg. That meant they no longer needed open water to reproduce, and could push farther inland, into places amphibians simply couldn't follow. The forests were doing more than housing animals, too. They were actively changing the entire planet, one buried layer at a time. Plants captured carbon dioxide, locked it into their tissue, and when they died in waterlogged ground, decomposition often couldn't fully break it down. Layer after layer got buried, and over enormous spans of geological time, some of that plant material became the coal deposits humans would eventually mine. When you burn coal today, you're releasing carbon originally captured by plants that lived hundreds of millions of years before dinosaurs even existed. But forests don't exist apart from climate. Continents kept drifting, and the Great Carboniferous wetlands wouldn't survive the shift that was already coming. As the Carboniferous gave way to the Permian, Earth's climate turned drier, and those vast wetland forests began to decline. Beneath all of this, Earth itself was rearranging the stage. Continents were gathering into one single, enormous supercontinent, Pangaea. One giant landmass, surrounded by a single global ocean, and its dry, harsh interior would push life into a dramatically different world. Then, around 252 million years ago, Earth experienced one of the most catastrophic events in its entire history. Massive volcanic eruptions struck what is now Siberia. These eruptions released enormous quantities of gas over an extended period. Carbon dioxide rose, the climate warmed, and ocean chemistry began to change. Oxygen levels in the ocean fell dramatically in some regions, and ecosystems that had thrived for hundreds of millions of years began collapsing. The result was devastating. The Permian-Triassic extinction became the single most severe mass extinction Earth has ever recorded. 252 million years ago, Earth was already a radically different planet. Its continents gathered into the single supercontinent, Pangaea. On land, reptiles were spreading into increasingly diverse environments. In the oceans, complex ecosystems had existed, stable, for hundreds of millions of years. Life had survived ice ages, rising seas, falling seas, and countless earlier disasters. But nothing had prepared it for what was coming next. Far to the north, magma forced its way upward, and lava spread across an enormous area. Not one volcano for an afternoon, but repeated eruptions for millennia. We call it the Siberian traps. The eruptions released enormous quantities of gas, warming the atmosphere and reorganizing Earth's entire climate system. Warmer water holds less dissolved oxygen, and changes in ocean circulation disrupted the movement of oxygen between the surface and the deep sea. In some regions, oxygen became scarce. In the most extreme places, it nearly vanished, and marine animals suddenly faced a world where breathing itself became difficult. Carbon dioxide also reacted with the ocean directly, making it harder for shell-building organisms, especially in coral reefs, to survive. Extinction rarely happens to just one species at a time. Ecosystems are networks. When one part collapses, everything depending on it starts to suffer too. Predators lost prey. Prey lost food. Reefs lost their builders. The extinction wasn't one event, it was becoming a chain reaction, cascading outward. The catastrophe wasn't confined to the oceans either. Rising heat, shifting rainfall, and collapsing food webs put enormous pressure on life across the land too. The scale of it was extraordinary. An estimated 80 to 90% of marine species disappeared. A large majority of land species vanished too. Entire lineages that had existed for tens, even hundreds of millions of years simply ended forever. You wouldn't know you were living through a mass extinction. You'd just notice food getting harder to find, and familiar species growing rarer, until they were gone. Yet life didn't disappear entirely. Some organisms survived, not necessarily the best ones, but simply the ones whose niches happened to remain viable. And here's one of the most important lessons of any mass extinction. Evolution doesn't select for what's best. It favors whatever can survive. Extinction had removed enormous amounts of competition, leaving entire ecological roles suddenly vacant. A predator's niche, a herbivore's niche, all standing empty. Life had survived, but the planet was now full of empty spaces. and empty spaces create opportunity. Survivors began to diversify into them. This is one reason mass extinctions are so often followed by bursts of new evolution. The world doesn't return to what it was. It becomes something new. Among the survivors were some reptile relatives and synapsids, the evolutionary group that eventually leads toward mammals. The world had been devastated. But evolution hadn't stopped. It was about to accelerate into a burst of diversification the wreckage gave no hint of. When you hear the word dinosaur, you probably picture something enormous and terrifying. But the very first dinosaurs looked nothing like that at all. They were relatively small, lightly built, and lived in a world already crowded with other reptiles. Dinosaurs weren't born kings. They had to earn their place. The Triassic period began right after the Great Dying, with Earth still recovering, and Pangaea stretching hot and dry across much of the planet. Dinosaurs shared that world with crocodile relatives, early mammals, turtles, and countless other reptiles. For millions of years, they were just one group among many. There wasn't one single magic advantage behind their eventual success. Several traits happened to work in their favor at once. Their limbs sat more directly beneath their bodies than in many sprawling reptiles, and their breathing systems were unusually efficient, with bird-like features already emerging. But perhaps most importantly, dinosaurs diversified. They didn't become one kind of animal. They became thousands of different solutions to survival. Some of the earliest dinosaurs, appearing in the late Triassic, were only around human size or smaller, already splitting into meat-eaters and plant-eating specialists. Dinosaurs didn't rise just because nothing challenged them, either. Earth changed again. The supercontinent split apart, with massive volcanic activity opening new ocean basins. Around 201 million years ago, another mass extinction struck, wiping out many competing groups. Dinosaurs survived, and the ecological stage opened wide for them. The Jurassic world became spectacular. Some dinosaurs grew into enormous herbivores. Others became specialized predators, evolution's most successful body plan yet. Then came the giants. Sauropods, with long necks, massive bodies, and remarkably efficient ways of supporting enormous size, among the largest land animals in Earth's history. Their long necks let them feed across a huge area without moving their entire body, and their teeth were built for cropping vegetation, not chewing it. Where there are giant herbivores, there are predators. Large theropods like Allosaurus filled that role inside a genuinely complex, competitive ecosystem. Above them, the sky belonged to pterosaurs, flying reptiles, close relatives of dinosaurs but not dinosaurs themselves, ranging from tiny to enormous. Below the surface, marine reptiles ruled the oceans. Ichthyosaurs built for fast swimming, and plesiosaurs with long necks and powerful flippers. Neither were dinosaurs either. Earth now held enormous ecosystems on land, in the air, and beneath the sea, all at the same time, something the planet had never managed before. But perhaps the strangest dinosaur story was happening quietly among the smaller predators. Some theropods evolved feathers, originally for insulation or display, not flight. Fossils like Archaeopteryx show a fascinating mixture of traits: feathers, wings, and a dinosaur-like skeleton all at once. Birds weren't living alongside dinosaurs. Birds were dinosaurs. And here's something people often forget. Mammals were already here too, quietly evolving for tens of millions of years, in their own small ecological spaces. Some were insectivores. Some climbed, some burrowed, some were active only at night. They weren't waiting for dinosaurs to disappear. They were already evolving on their own path. The Jurassic gave way to the Cretaceous. Continents kept drifting apart, and flowering plants spread and diversified, transforming entire food webs. Dinosaurs kept evolving too. Horned herbivores, duck-billed dinosaurs, armored dinosaurs, and among the predators, one lineage that would become genuinely famous. Tyrannosaurus rex, one of the most famous animals that ever lived. But it wasn't a movie monster. It was a real animal competing, healing, raising offspring. And then there's Velociraptor. Forget the movie version. The real Velociraptor was much smaller than you'd expect, and covered in feathers. It lived in what's now Mongolia, part of a diverse family of feathered predatory dinosaurs, many with sickle-shaped claws built for hunting, not for looking terrifying on screen. This is the most important thing to understand about the Age of Dinosaurs. It wasn't a world of monsters. It was a world of interlocking ecosystems. Herbivores ate plants. Predators hunted herbivores. Scavengers cleaned up the remains. Dinosaurs occupied nearly every major terrestrial role, an entire ecological empire. Their history stretched across more than 160 million years, long before humans, long before the Himalayas had even risen, generation after generation. But no dynasty lasts forever. Earth's climate was shifting, continents were moving, and somewhere beyond the atmosphere, something was already moving toward Earth. It had been traveling through space for millions of years, and when it finally arrived, the Age of Dinosaurs would change forever. 66 million years ago, Earth was having an entirely ordinary day. The sun rose, rivers flowed, herds searched for food, and predators searched for prey. Somewhere above all of it, something was coming. Not a comet, not a planet, but an asteroid, several kilometers across, a leftover piece of the solar system. It had been orbiting the sun for millions of years, until its orbit finally intersected Earth's. Nothing on the planet could have seen it coming. The asteroid entered Earth's atmosphere at extraordinary speed, heating the air violently. For the animals below, the sky suddenly turned terrifyingly bright. It struck near what is now the Yucatan Peninsula in Mexico, excavating a crater roughly 180 kilometers across, in moments, releasing energy almost instantly. The impact triggered a chain reaction. Massive seismic waves tore through the crust, and the nearby sea sent enormous waves racing outward. Enormous quantities of pulverized rock were thrown high into the atmosphere, some of it destined to travel all the way around the planet. As that material fell back to Earth, it heated the sky again, sparking wildfires. For survivors of the initial blast, the disaster was only beginning. But the most devastating consequence wasn't the explosion itself. It was what happened to the atmosphere afterward. Fine particles blocked sunlight from reaching the surface. Daylight weakened, temperatures fell, and now we reach the single most important part of the entire extinction. Photosynthesis depends on light, and light had just been cut off. Plants struggled, plankton declined, and when the very base of the food chain collapses, everything built on top of it feels the consequences immediately. Imagine removing the ground floor of a building. Eventually, every floor above it has nothing left to stand on. Herbivorous dinosaurs needed enormous amounts of vegetation, and as plant life collapsed, their food vanished. Predators, depending on those herbivores, collapsed right behind them. But extinction wasn't universal. Small mammals survived. So did some birds, turtles, and crocodilian relatives, along with countless insects, for reasons still being studied today. One survivor mattered enormously to the rest of this story: birds. Here's the strange part: when people say, the dinosaurs went extinct, that isn't completely true. One branch survived: the avian dinosaurs, ancestors of every bird alive today. Dinosaurs never actually vanished completely. One lineage simply made it through. We don't know every detail of why birds specifically survived, but small body size, flexible diets, and the ability to exploit seeds likely all helped. Whatever the exact combination, their survival changed the entire future of life. The asteroid didn't just destroy the old world, it opened the door to a new one. The large non-avian dinosaurs were gone, along with many other dominant reptiles. Entire ecosystems had been erased in what was, geologically, an instant. But surviving mammals inherited a planet suddenly full of ecological space. And over the next tens of millions of years, they were about to diversify dramatically. The asteroid had changed the planet, but it hadn't stopped evolution. In the darkness, small mammals had survived, and now they faced something rare: opportunity. Mammals weren't newcomers, though. They'd been evolving for more than 200 million years already, living quietly alongside dinosaurs the entire time. Imagine a city where almost every building suddenly stands empty. The city hasn't disappeared. The opportunities have simply multiplied. That's what happened to Earth's ecosystems. Many large animals were gone, and many ecological roles stood vacant. Surviving mammals began expanding into them, as selection acted on a completely changed world. Over millions of years, mammals diversified enormously. Some stayed tiny, others grew enormous, some became predators, some returned to water, some took to the sky. One group became extraordinarily successful almost immediately: rodents, whose continuously growing incisors made them remarkably effective wherever they went. Today, rodents live in deserts, forests, grasslands, mountains, and even our own homes. One evolutionary experiment producing an astonishing number of species. But every expanding herbivore population creates another opportunity: predators. Mammals evolved sharp teeth, powerful jaws, speed, and endurance. Different solutions to the same problem. And mammals didn't stay small for long. Once the ecological landscape changed, some grew enormous, occupying roles that giant dinosaurs had once filled entirely. One lineage left the land altogether and would eventually become the largest animals ever known: whales. But whales didn't begin in the ocean at all. Their ancestors were terrestrial mammals with legs that could walk on land. Fossils show a transition into increasingly comfortable shallow water living. Bodies changed. Nostrils shifted backward, limbs adapted for swimming, and eventually their descendants became fully marine, a land mammal transformed into an ocean giant. On land, another group grew enormous too. The proboscideans, the lineage that eventually produced elephants, their trunks becoming one of evolution's strangest tools. The horse tells a similarly surprising story. The earliest members of that lineage were small, forest-dwelling animals with multiple toes on each foot. Over millions of years, as open grasslands spread, the lineage evolved specialized teeth and limbs built for speed, one of evolution's most recognizable running machines. Then there were the bats, the only mammals capable of true powered flight. Their forelimbs elongated into wings, and some evolved echolocation, an entirely different way of sensing the world. Look at what happened. One branch of life produced animals living in nearly every environment on Earth: desert, ocean, forest, mountain, and even open sky. But one particular branch matters most for our story: the primates, mammals that adapted to complex, three-dimensional forest environments. Above the ground, branches connected to branches, and falling meant real danger. So grasping hands, flexible limbs, and sharper brains all became genuinely valuable. Not because evolution was trying to create humans. There was no destination and no finish line. Just organisms, environments, variation, and selection, generation after generation. This is one of the most important ideas in the entire story. Evolution doesn't work toward perfection. It doesn't know humans, whales, or bats are coming. The whale, the elephant, the bat, the horse, and the primate, none of them are stepping stones toward us. They're branches of the very same experiment. But one of those branches would eventually leave the trees, walk upright, make tools, control fire, and eventually look backward and ask how any of this began. Cities hadn't been imagined yet. Language hadn't been spoken. Humanity itself was still millions of years from existing. A very different world entirely. And somewhere in that world, our own ancestors were just beginning a journey that would take millions of years to complete. There was no single moment when the first human was born. Not one species suddenly appearing, but millions of years of gradual experiments that produced us. You might expect to find a moment when a mother gave birth, and suddenly, a human existed. But evolution doesn't work that way at all. There wasn't one morning when an ape woke up and became human. Instead, generation after generation, population after population, changed gradually, almost imperceptibly. Our story begins in Africa, not because primates only lived there, but because the specific lineage that led to us evolved on that continent. African environments were changing. Forests expanding and contracting, grasslands spreading, and our ancestors faced an increasingly variable, unpredictable world. Then something extraordinary happened. Our ancestors became habitual bipeds, walking upright on two legs. We still don't know exactly why. It may have helped with efficient movement, or freed the hands for carrying food and infants. There was no single switch. It evolved through a whole sequence of changes. One of the most famous early hominins, Australopithecus afarensis, lived roughly 3 to 4 million years ago, a genuine mixture of traits. Its brain was much smaller than ours, and its arms still showed adaptations for climbing. But its pelvis, legs, and feet were clearly built for walking. Around 3.6 million years ago, at Laetoli in what's now Tanzania, hominins walked across wet volcanic ash and left their footprints behind. The surface was buried, and millions of years later, we found them. For a moment, you can almost watch our ancestors walking across the ancient Earth. Brain size increased across the Homo lineage. Hands changed, diets changed, and eventually something happened that left real physical evidence behind. Deliberate stone tools. Early stone technologies appear in the record by at least 2.6 million years ago. One stone struck against another, until a sharp edge appears. One early species, Homo habilis, is traditionally linked to these early stone tool cultures. Though human evolution is genuinely messy, species boundaries are still actively debated. Then comes one of the most important species in our entire history, Homo erectus, which survived for more than 1 million years. Longer legs, more human-like proportions, larger brains, and increasingly sophisticated tools. Some populations even produced carefully, deliberately shaped hand axes. And then our ancestors began controlling one of nature's most powerful forces: fire. Exactly when this became routine is still debated, but its impact wasn't. Fire brought heat, light, protection, and eventually, cooking, changing what humans could eat, where they could live, and how they interacted after dark. For the first time in this entire story, the night itself became part of the human world, instead of simply something to hide from. Homo erectus and related populations reached parts of Eurasia remarkably early, moving into unfamiliar climates, new predators, and entirely new food sources. Human evolution was no longer happening in one single place. It was becoming genuinely global for the very first time. And here's where the story gets even more surprising. For much of human prehistory, different kinds of humans lived on Earth at the very same time. They weren't simply stages in one straight line. They were separate branches. Some disappeared, some met each other, and sometimes they had children together. The Neanderthals lived across Europe and Western Asia, surviving ice ages, hunting large animals, making sophisticated tools, and caring for injured members of their own groups. They weren't the primitive caricature you might picture. They were intelligent human relatives, adapted to some of the harshest environments Earth had to offer. Then came a discovery that changed the story again. Tiny bone fragments in a Siberian cave, revealed by ancient DNA to belong to an unknown human population, the Denisovans. Their story is still being reconstructed, but their genetic legacy survives in some populations alive today. The human family tree turned out far more tangled than expected. Eventually, in Africa, our own species emerged, Homo sapiens. Anatomically modern humans appear in the fossil record hundreds of thousands of years ago. But we didn't instantly become the humans we recognize today. There was no sudden transformation. Our species simply kept on evolving, like every lineage before us. Some Homo sapiens populations eventually expanded beyond Africa, into Eurasia, then Southeast Asia, Australia, Europe, and eventually the Americas. When they arrived in Eurasia, the world wasn't empty. Neanderthals were already there, and Denisovan populations lived across parts of Asia. These groups didn't simply avoid each other. Sometimes they met, and sometimes they had children together. Their descendants carrying those genes forward into us. Which means the story of our species contains pieces of the stories of other humans, too, quietly written into the DNA of people alive right now. Look at yourself. You are not the beginning of this story. You are the result of it. Your DNA carrying a history through countless generations. We learned to walk. We learned to make tools. We learned to control fire. We survived ice ages, met other humans. And eventually, we became the only human species left. Humans didn't become powerful because we were the strongest animal on the planet. Something else entirely explains how we ended up everywhere. Today, almost every continent is connected by roads, ships, and airplanes. But imagine Earth stripped of all of it. Just an enormous, unexplored planet. Homo sapiens had already existed in Africa for hundreds of thousands of years before some populations began expanding beyond the continent entirely. They moved through deserts, mountains, forests, and coastlines their ancestors had never seen, eventually reaching Asia, Australia, Europe, and the Americas. The move into Sahol, the Ice Age landmass including Australia and New Guinea, required crossing open water on purpose. That means these humans weren't simply wandering wherever land continued. They were capable of planning, building, and cooperating enough to enter an environment they couldn't just walk into. Then came one of the greatest environmental challenges humans have ever faced. The Ice Age, with much of the northern hemisphere dramatically colder than today. Humans lived there anyway. They hunted, built shelters, controlled fire, and made clothing, surviving conditions that would be instantly lethal to an unprotected human body. Here's the strange thing. Humans are physically unimpressive compared to the animals around us. No claws like a bear. Not especially fast. Can't fly. Without technology, we're not particularly well suited to extreme environments at all. But humans had something else that mattered more. Each other. A single human is vulnerable. A group of humans can be remarkably powerful. One person discovers something, another remembers it, another teaches it, another improves it. Knowledge didn't have to die with the person who discovered it. It could accumulate, generation after generation, in a way no other animal on Earth could manage. Consider hunting a large, dangerous animal. Humans could coordinate the actions of many individuals at once, tracking, predicting where prey might go, communicating the entire plan. The real advantage was never one person's strength. It was the group's ability to behave like a single, coordinated system. And humans kept improving their tools too. Stone became sharper, wood became weapons, bone became needles, letting people make fitted clothing for the very first time. A spear gave humans reach, a needle gave precision, a boat gave mobility, fire gave heat. Technology was effectively expanding what the human body could do. But tools alone can't explain the human explosion. There was another technology, one you can't even see: language. Language lets one human mind directly influence another, describing something that isn't physically here, something that happened yesterday, or something that might happen tomorrow. You can warn someone, teach a skill, tell a story, and perhaps most importantly, create a shared reality inside the minds of an entire group at once. Imagine sitting around a fire tens of thousands of years ago, listening to someone describe a dangerous place, a successful hunt, or where water can be found. A child doesn't need to rediscover everything from scratch. They inherit knowledge without inheriting the actual experience. An extraordinary evolutionary advantage. Then humans began leaving behind something even stranger: images. Animals' hands, symbols, geometric patterns. We don't know exactly what every ancient image meant. But they tell us something important. Humans weren't simply responding to their immediate environment anymore. They were making objects stand for ideas. They were creating meaning. Humans made music too. Ancient bone flutes have survived as evidence. Music doesn't provide food or make you run faster. Humans made it anyway, because they weren't only surviving. And then there's something even harder to explain. Humans sometimes deliberately buried their dead, occasionally placing objects alongside the body. We can't know exactly what every burial meant: memory, identity, grief, belief. But something had clearly changed. Humans were thinking about people no longer even alive. This may be one of our most unusual abilities. Imagining things that aren't in front of us, and then acting together as though that imagined thing were real. Eventually, humans reached the Americas too, likely crossing land exposed by lower ice age sea levels near the Bering Strait, spreading south over many generations. They encountered a world filled with giants along the way: mammoths, giant ground sloths, saber-toothed predators, and in Australia, enormous marsupials. Many of those animals disappeared during this period. Climate change played a major role, and in several regions, human activity clearly contributed too. In a remarkably short span of geological time, humans had adapted to an extraordinary range of environments: Arctic cold, tropical forest, desert, and open ocean. Our bodies barely changed to survive each one. Our culture did all the work instead: clothing, shelter, fire, boats, tools, knowledge, and stories. What really made Homo sapiens so successful was never one single thing: intelligence, language, and tools, combined and compounding across generations. One generation could inherit knowledge from the last, improve it, and pass that improvement forward. Over thousands of generations, small improvements became enormous transformations. But humans were still hunter-gatherers in most places, moving with the seasons, following animals, collecting plants, living in relatively small communities. Until one of the biggest transformations in all of human history began with something incredibly small. Why would a species that had survived for hundreds of thousands of years, by following nature, suddenly decide to stay in one place and change it instead? Look around you right now. Almost everything you need to survive is sitting on a shelf somewhere. For nearly all of human history, none of that existed. No farms, no supermarkets, no fields stretching to the horizon anywhere on the planet. Most humans lived as hunter-gatherers, collecting whatever the environment provided. And here's something important. Hunter-gatherers weren't simply desperate people waiting for civilization to rescue them. Many societies developed sophisticated knowledge of their own environments. They knew which plants were edible and which were poisonous, where animals moved, where water could be found, how to survive without any permanent infrastructure at all. The reason was the planet itself changing. The last ice age was ending, global climate warmed, ice sheets retreated, and sea levels rose. Ecosystems shifted, and humans had to adapt once again. But this time, instead of just gathering plants, some people began deliberately planting them. Perhaps it started by accident. Seeds discarded near camps, growing again on their own. We don't know exactly how every early farming system began. And it didn't happen in just one place. Farming emerged independently in several different parts of the world on completely different crops. In the Fertile Crescent, people domesticated wheat and barley. In China, rice and millet became central crops. In the Americas, maize, and in the Andes, potatoes. Agriculture wasn't one single invention. It was a series of separate human experiments, conducted independently across thousands of years, on different continents. And something even stranger happened alongside it. Humans didn't just plant crops. We started changing them, saving seeds from plants with bigger yields. Over many generations, those repeated choices altered the plants themselves. Evolution had found a genuinely new force acting on it: human selection. Plants weren't the only thing we changed, either. We formed long-term relationships with animals too, starting with the dog, descended from ancient wolf populations. Dogs became hunting partners, guards, and companions. Later came livestock in different regions: goats, sheep, cattle, and pigs, each part of a new human economy. Farming created a new possibility too. If food could be produced in one place, humans didn't always need to keep following it around. They could simply stay. Houses became permanent. Storage became genuinely important. Humans were changing from a species that constantly moved into one capable of reshaping a specific piece of land. And then something predictable followed. More food supported more people meant larger communities, which needed still more food, and the cycle kept feeding itself. Agriculture also created something hunter-gatherers usually couldn't produce at the same scale: surplus, food that could be stored well beyond today. And that changed everything, because if some people could produce more food than they immediately needed, not everyone had to spend every waking hour finding it. Some people could become builders, potters, trillagers, religious specialists. Human society was becoming genuinely specialized for the first time in its history. This created something powerful: interdependence. People increasingly relied on complete strangers for things they could no longer produce entirely by themselves. But staying in one place created a new problem too. Land became valuable. A hunter-gatherer can move to another resource. A farmer has already planted crops in one place. Suddenly, there was far more to defend: land, crops, animals, houses, and stored food, all sitting still, all vulnerable in a way they'd never been before. Agriculture also created real opportunities for inequality. Some families accumulated more land, more animals, and more wealth. Differences that could now be passed down. And with wealth came something else entirely: conflict. When people settled permanently, there were finally things genuinely worth fighting over: land, water, and eventually, power itself. But settlement didn't only create conflict. It created connection too. Communities began exchanging stone, shells, minerals, and ideas they couldn't easily obtain on their own. A village could become part of a much larger network, and networks have one property that matters here: they can keep growing, almost indefinitely. Villages became towns. Towns became cities, with thousands of people now living together, needing food systems, water construction, trade rules, and real leadership. Once societies grew large enough, food itself became a form of power. Whoever controlled the stores could influence everyone who depended on them. Agriculture didn't automatically create civilization on its own, but it created the exact conditions where larger, more complex societies could finally emerge. Farmers produced food. Surplus supported specialists. Specialists created technology. Trade connected communities. And eventually population created cities, with administration and records. Until this point, almost everything humanity knew had to survive purely inside human minds: memories, stories, and skills, passed from person to person. Then humans discovered a way to store information entirely outside the brain. A mark in clay, a symbol carved into stone. Humanity had invented a second memory. Suddenly, a human could speak to someone hundreds of kilometers away, or to someone who hadn't even been born yet. Humans could finally begin leaving behind history. A few thousand years earlier, a human settlement might have been little more than a handful of houses, where everyone knew everyone else by name. But now, something fundamentally different was emerging. Thousands of people living together, most of whom had never even met, with different jobs, wealth, and power. Humanity had entered the age of civilization. And notice something about nearly all of the world's earliest ones. They grew up beside rivers. Rivers carried water, fertile sediment, and fish, each civilization developing its own answer to one enormous shared challenge. How do you organize thousands of people at once? Our first stop is Mesopotamia, literally, the land between rivers, the Tigris and the Euphrates. Some of the earliest cities on Earth emerged here. One in particular became especially important. Uruk, one of the world's earliest major cities, home to farmers, craftspeople, traders, and religious officials. And administrators there had a growing problem. Who received grain? Who owed grain? Humans needed a memory that couldn't forget. This is where one of humanity's greatest inventions emerged: writing. The earliest writing systems weren't poetry, they were pure administration. Food, animals, labor, numbers. A clay tablet could remember something long after the person who recorded it had walked away. And that changed what an entire society could organize. Cities didn't always cooperate, either. Mesopotamia became a landscape of competing city-states, fighting over land, water, trade, and power. And when thousands of people live together, another problem appears. What happens when people disagree, or someone steals, or two people make conflicting claims? Ancient Mesopotamian societies developed written legal traditions. The most famous surviving example, though not the earliest, is the Code of Hammurabi. Now travel thousands of kilometers west to another great river, the Nile. Egypt was built along its yearly flood, which brought water, soil, and reliable transport. Over time, Upper and Lower Egypt were unified under a single kingship, becoming a remarkably centralized state, with the pharaoh at its absolute center. Egyptian kingship was deeply tied to religion and cosmic order, with the pharaoh at the center of both. Politics and belief thoroughly intertwined. And then Egypt built something that still seems almost impossible. The Great Pyramid at Giza, raised more than 4,500 years ago from millions of carefully surveyed stone blocks. It wasn't simply a pile of stones. It was proof that a state could coordinate an enormous workforce. Cooperation turned directly into architecture. While Egypt and Mesopotamia were developing, another urban civilization was emerging farther east, in the Indus Valley. Cities like Harappa and Mohenjo-daro. Their cities reveal careful planning. Streets laid out on a grid, standardized bricks, wells, and sophisticated drainage systems. Some houses even had private bathing areas. These weren't accidental clusters of houses. They were deliberately planned urban environments, thousands of years before most of the world attempted anything similar. And then comes one of archaeology's great unsolved mysteries. The Indus civilization left thousands of inscriptions, but their script has never been securely deciphered. We can see the symbols, we can study where they appear, but we still can't confidently read a single word of the language behind them. Imagine finding an entire library and being unable to read a single page of it. That mystery remains genuinely unsolved even today. Farther east still, along the Yellow River, another center of complex society developed. And by the 2nd millennium BCE, the Shang dynasty ruled a powerful Bronze Age state. Bronze changed the possibilities of warfare, ritual, and craftsmanship, but it needed raw materials and skilled workers. Whoever controlled that system held real power. The Shang also left something enormously important: written records, carved onto oracle bones, and unlike the Indus script, this one can still be read. Civilization wasn't only about food and kings either. Humans began looking upward, noticing that the sun, moon, and stars moved in recurring, predictable patterns. That predictability could organize a calendar. When to plant, when seasons would change, when floods would arrive. The sky had become a giant, dependable clock. And running a civilization meant you needed numbers too. How much grain is stored? How much land does someone own? How much tax is owed? Mathematics became a genuinely practical technology of civilization, letting humans measure, count, calculate, and build at a scale no single mind could track alone. 4 very different civilizations, 4 very different environments. Mesopotamia's competing cities, Egypt's centralized kingdom, the Indus Valley's planned engineering, and China's bronze and writing. But they all shared the same underlying pattern. Food created surplus, surplus supported specialists, and trade demanded organization. Organization that built institutions with real power. Bigger societies created bigger possibilities, but they also created bigger problems. Inequality, forced labor, warfare, and environmental damage arriving alongside every genuine advance. Remember where we began. One human being, a body made from atoms forged in ancient stars, belonging to a small community. Then villages became cities. And writing gave humanity something even more powerful than memory across one lifetime. The ability to remember across thousands of years. A city can control the land around it. A kingdom can control many cities. But eventually, something much larger becomes possible. An empire. An empire has to solve a much harder problem than conquest alone. How do you rule enormous distances and govern people who aren't like you at all? One great early example came from Persia, the Achaemenid Empire, beginning with Cyrus the Great in the 6th century BCE, spanning much of the ancient Near East. Conquering territory is easier than governing it, though. Persia built roads and messengers, turning raw conquest into an actual functioning network. Just to the west, Greece took a very different approach, dividing into independent city-states like Athens and Sparta, who fought, traded, and shared one common culture. Then one young king changed the map entirely. Alexander of Macedon, whose armies conquered the Persian Empire in a remarkably short span of time. Alexander died young, and his empire didn't survive him intact. But something else did. Greek culture spread across Egypt and Persia, creating the Hellenistic world. Meanwhile, another city was growing. Rome, which began as a single city-state, and eventually became one of the most powerful political systems the ancient world had seen. Rome expanded through Italy, then across the Mediterranean, until the Mediterranean itself felt like the center of the entire world. But Rome's real power wasn't only its army, it was infrastructure. Roads, aqueducts, and Roman law, letting soldiers move and merchants move right behind them. Far to the east, India was building its own enormous political experiment. The Mauryan Empire unified much of the subcontinent under one powerful, centralized state. After the brutal conquest of Kalinga, Emperor Ashoka's policies changed dramatically, turning toward Buddhist teachings and moral governance. His messages were carved onto rocks and pillars across the empire. The state was no longer communicating just orders. It was communicating ideas. Farther east, China was experiencing its own transformation. The Qin state conquered its rivals, and in 221 BCE, became the first unified imperial dynasty in Chinese history. The Qin dynasty was short-lived, but imperial unification survived. The Han dynasty built on it, expanding government and agriculture across an enormous population. And now something genuinely important begins to happen. Long-distance trade networks connect China, Central Asia, India, and the Mediterranean. The Silk Road. Silk traveled west, horses traveled east, but the most valuable cargo wasn't always physical. Ideas traveled along exactly the same routes. Not every great civilization connected to these Eurasian empires either. Thousands of kilometers away in Mesoamerica, Maya civilization developed entirely independently. Their achievements remind us of something important. Humans didn't need one civilization teaching all the others. Different societies solved the same problems in different ways. More than 1,000 years later, another empire created one of the largest contiguous land empires in history, the Mongols, beginning with Genghis Khan. The conquest was extraordinarily violent, but the empire also created a period of unusually intense connection across Eurasia, along those very same routes. Centuries later, the Ottoman Empire emerged at one of the most important crossroads on Earth, connecting territories across Europe, Asia, and Africa. Look at what's happening across all of this. A road built for an army can later carry merchants. An idea can travel farther than the person who invented it ever could. But there's a darker side, too. The same routes that carried silk could carry armies. The same roads that carried ideas could just as easily carry disease. Human connection has never been purely good or purely bad. It has always, stubbornly, been both at once. By this point, humans had built cities on every inhabited continent, developed writing, measured the heavens, and carried ideas between distant civilizations. But the planet was still only loosely connected. Vast oceans separated entire civilizations, and news could take months just to travel between them. For thousands of years, human societies had been building increasingly sophisticated networks. But humans were about to do something that would change the planet forever. They were about to cross the largest oceans and connect entire worlds that had evolved separately for thousands of years. Nothing would ever be the same again. Imagine being born 1,000 years ago. You'd probably live in a world that looked remarkably similar to the one your own parents knew. Knowledge had always been powerful, but it had one huge problem. It was expensive to reproduce. Copying a single book by hand could take months or years. Then, in 15th century Europe, Johannes Gutenberg's printing technology transformed the economics of reproducing text. The same words, copied thousands, then millions of times. Knowledge could travel farther, faster, and more cheaply than ever before. humanity finally had something approaching a real mass information network. But information alone wasn't enough. Humans needed a new way of asking questions. Not, what does tradition say? But, what does nature actually do? During the scientific revolution, Copernicus, Galileo, and Kepler transformed our understanding of the heavens. And then came Isaac Newton, who showed that falling apples and orbiting planets obeyed the same laws. Suddenly, the universe itself looked mathematically understandable. And if nature obeyed predictable rules, humans could learn to use them directly. Engineers eventually learned to use steam pressure to perform mechanical work, a machine that could convert heat directly into motion and motion into useful labor. In Britain, and eventually elsewhere, industrialization transformed production entirely. Factories concentrating machines, workers, and energy at a scale earlier societies could barely imagine. It created enormous wealth. It also created dangerous working conditions, brutally long hours, and child labor. Progress and disruption arriving together, as always. Then steam escaped the factory and entered transportation. Railroads connected cities faster than any previous form of transport. A journey that once took days now taking only hours. But even the fastest train still had to physically travel. Then humans discovered something extraordinary. Information could travel as an electrical signal instead. The telegraph. Messages could now cross entire continents in minutes, rather than weeks. The world had begun communicating at the literal speed of electricity. Then came another leap, sending the human voice itself. The telephone turned sound into a signal, and back into sound, somewhere else entirely. Electricity became a new infrastructure for all of civilization. Factories running on electric motors, streets lit at night, cities finally able to grow upward. Then humans put engines on wheels. The automobile transformed personal transportation completely. Within a few generations, the machine had replaced the horse almost everywhere. Then came an achievement people had dreamed of for thousands of years: flight. In 1903, the Wright brothers achieved the first powered flight, lasting only seconds. Within decades, humans were crossing entire oceans by air. Within a few more, we were carrying hundreds of people across continents in a matter of hours. Perhaps the most important revolution of all wasn't transportation, though. It was happening inside the human body. For most of history, disease was simply mysterious. Then microscopy revealed an invisible world of microorganisms. Germ theory transformed medicine. Vaccination, sanitation, and eventually antibiotics, all fighting diseases that had terrified humanity for millennia. And then humans built a machine that would change the nature of information itself: the computer. At first, room-sized, slow, and extraordinarily expensive. Then came the transistor, then integrated circuits, then microprocessors, and suddenly, computation was no longer something only governments and research labs could afford. But computers eventually started talking to each other. Networks connected to other networks, until the internet linked billions of people almost instantly. Information that once took months to cross the planet could now do it in milliseconds. One person reaching another on the opposite side of Earth, without either one moving. Look at what just happened across this single chapter. Humans moved at the speed of their feet, then ships, then trains, then at the speed of electricity itself. And here's the real pattern. Each invention began helping create the next one. The printing press spread knowledge. Knowledge produced science. Science accelerated everything after it. This was no longer ordinary technological change. It had become a genuine feedback loop, each new tool making the next one arrive faster than the last. Look at the timeline of our entire story. The universe is 13.8 billion years old. Almost everything you recognize as modern appeared within an impossibly thin sliver at the very end. We went from stone tools to cities, from cities to factories, from factories to computers, from computers to a planet connected almost instantly. And now we reach a strange moment in the human story. For almost all of history, the biggest force humans could control was fire, then steam, then electricity. We're now building machines that process information in ways that increasingly resemble some of the things our own brains do. Artificial intelligence. We've reached something our ancestors could never have imagined. A civilization whose greatest invention may turn out to be intelligence itself. But technology is only half the story. Every invention changed how we lived, loved, and understood ourselves too. So now we have to return to the smallest part of this entire, enormous story. You. Imagine living 500 years ago. To speak to someone far away, you had to send a physical object, carried by hand, sometimes taking months to arrive. Then humans discovered a way to make information travel without carrying it at all. Radio, converting a human voice into a signal and reconstructing it somewhere else. Suddenly, someone thousands of kilometers away could hear a voice that traveled there on nothing at all. Not a letter, not a writer, not a ship. Radio also created something new. Millions of people receiving the exact same message at the exact same moment. A shared experience the planet never had before. Then television added images to the sound. A person at home could watch a war, an election, or a discovery unfolding thousands of kilometers away. There was still a problem, though. Signals were limited by the shape of the planet itself. So humans did something extraordinary. They put machines directly into space. Satellites changed communication, navigation, and weather forecasting all at once, bouncing signals across space and watching storms form from high above the surface. But the real revolution came when computers began talking to each other. Networks connected to other networks, and the internet emerged as one single global system. Information stopped being trapped inside individual machines. A document, a photograph, a conversation, almost anything digital could now move freely through the network. Physical distance still existed, but informational distance was collapsing. You could read something written on the other side of the planet, almost instantly. Then computers became small enough to fit in a pocket. A modern smartphone isn't really a phone at all. It's a camera, a map, a library, a bank all at once. Beneath the surface, the world was starting to share production too. Parts made in one place, shipped everywhere, the same way information already moved. Then humans did something profoundly different. We left the planet entirely and looked back at it. From space, borders simply disappear. Countries become invisible. For billions of years, Earth existed without humans at all. Then one species began building connections across the entire surface: roads, cables, satellites, mines. There was one more step still coming, though. A machine that could learn patterns from enormous amounts of information, doing far more than storing or sending it. This was the beginning of a new kind of technology entirely. Artificial intelligence. A machine that could recognize, generate, and reason about information. Every major technological revolution gave humans a new capability. But artificial intelligence introduces something different. It interacts directly with the actual work of our minds. Think about how strange this moment really is. A person can sit alone in a room, hold a device smaller than their hand, and reach almost anyone on Earth instantly. None of this would have been imaginable to the overwhelming majority of every human who has ever lived, across the entire span of our species. We spent thousands of years building roads between cities, then cables between countries, then satellites around the planet, and finally, connected billions of human minds. We didn't just make the world smaller. We turned the entire planet into a single network. But there's something we still haven't explained. Out of all the billions of humans connected to this network, each one still experiences the world from inside exactly one single brain. How did that even happen? Before there were humans, there was no one here to watch any of this happen. Stars were born, stars died. None of it needed an audience. Earth existed for billions of years before humans appeared. Dinosaurs lived here for more than 150 million years. None of them ever needed to know the age of the universe. But evolution produced something unusual. Organisms increasingly capable of sensing their surroundings, and eventually, a nervous system complex enough to build a model of the world. You don't experience the world directly. Light enters your eyes, and your brain constructs an entire experience from nothing but electrical signals. And then your brain does something even stranger. It doesn't only perceive the present. It remembers a past that isn't here, and imagines a future that hasn't happened yet. Humans can do something else entirely. Imagine a tool before building it, a city before constructing it, a journey before ever taking it. Then humans develop language, letting one brain transfer an idea directly into another. And eventually, we learn to preserve those ideas outside the brain entirely. Drawing symbols, writing, books. An idea could now survive its own creator. A person could die, while their ideas kept traveling forward through time. Eventually, millions of connected minds could collectively reconstruct a story stretching back roughly 13.8 billion years. This exact story. And here's where it becomes personal. Look at your own body. The carbon in your cells was forged through generations of dying stars. The oxygen you just breathed, the calcium in your bones, the iron in your blood, all of it is part of that same cosmic chemical history. When you were born, the universe didn't manufacture new atoms just for you. Those atoms were already ancient. They'd simply been somewhere else first. They moved through stars, through rock, through ocean, through other living things, and eventually, through you. So when you look up at the night sky, you aren't looking at something separate from yourself. You're looking at the same universe that produced your planet, produced life itself, and produced the exact brain you're using to understand any of this right now. You are not outside this story. You are part of it. And for one brief moment, the universe has produced something capable of knowing that it exists at all. 13.8 billion years brought us here. Now let's try something much harder, figuring out what happens next. The past leaves evidence, fossils, rocks, written records, light from distant galaxies. We can reconstruct exactly what happened. The future offers none of that. We can predict some things and estimate probabilities. But nobody actually knows what humanity becomes from here. And that uncertainty isn't a weakness of the story. It is the story. The first challenge is the planet itself. Humanity built an extraordinary civilization using enormous energy, and in the process, changed the composition of the atmosphere. Human-driven greenhouse gas emissions are warming the planet right now. The future climate depends heavily on what we choose to do next. For thousands of years, humans built tools to extend physical power. Computers extended something different: our ability to process information itself. We're now building systems that can learn patterns from enormous amounts of data, recognizing images, generating language, and assisting with genuinely complex scientific work. That could dramatically increase what any individual human is capable of. But powerful technology creates powerful risks too: misuse, misinformation, and unanswered questions about control. We're also learning to manipulate biology directly, reading and modifying genetic material, and developing therapies for diseases once considered completely untreatable. That raises difficult questions of its own. Should we only repair disease or actively enhance human ability? Who gets access and who decides? Technology doesn't make humanity invulnerable either. Asteroids have struck Earth before. Massive volcanic eruptions have reshaped the planet before. Both can happen again. Humans are already learning to detect some of these threats, tracking near-Earth objects, and even testing whether an asteroid's path can be deliberately changed. But perhaps the biggest question about our future isn't how we survive on Earth. It's whether we ever become a civilization that lives beyond it. We've already taken our first steps, living in orbit, walking on the moon, and sending robotic spacecraft across the entire solar system. Mars is often imagined as humanity's second home. It isn't. Mars is brutally hostile: a paper-thin atmosphere, a cold surface, and serious radiation exposure. Humans there would need artificial habitats, constant power, and food production. Mars wouldn't be another Earth. It would be another experiment in human survival. Think about the pattern, though. Our ancestors spread across Africa, then continents, then oceans, then the atmosphere, and eventually into space itself. Becoming a spacefaring species would be the beginning of something, not the end of it. Space is enormous. Even nearby stars are unimaginably far away. Now imagine something harder still. Not 100 years from now, but thousands. Languages could change beyond recognition. Nations could vanish. New cultures could emerge. The people of that future might look back at us the way we look back at ancient civilizations: strange, distant, and almost unimaginable. Will future humans still be biologically similar to us at all? Will technology merge with our own bodies? We simply don't know. We've spent this entire story looking backward, with the benefit of evidence. But beyond this exact moment, the story is still being written, one choice at a time. We usually imagine Earth as something permanent: mountains, oceans, continents, cities, all fixed in place. But it isn't. Earth has never once been still. Zoom into deep geological time, and the continents themselves begin to move. Enormous tectonic plates drifting only centimeters a year, slower than your fingernails grow. But over millions of years, a few centimeters becomes thousands of kilometers. Earth has repeatedly assembled and broken apart, entire supercontinents. Given enough time, the continents may reassemble again into some future supercontinent. Nobody knows exactly what shape it will finally take. When continents move, oceans move with them too. And because oceans transport enormous amounts of heat, that alone can transform the entire global climate. Earth's climate has never been constant, either. Ice ages and volcanic episodes have all reshaped it before. Today, one additional force has become extraordinarily important: us. Over the last few centuries, humans have dramatically increased greenhouse gases in the atmosphere, warming the planet and pushing ecosystems into entirely new conditions. But here's the important part. Even if humans disappeared tomorrow, Earth wouldn't stop changing. The planet doesn't need us to continue. Somewhere in Earth's future, two continents may collide, mountains rising, then slowly worn down, until millions of years later, the range is simply gone. On truly long timescales, even mountains are temporary. Life will keep changing right alongside the planet, some species adapting, others disappearing entirely. But eventually, there's a force no technology on Earth can permanently hold back. Our own sun, which, like every star, is slowly changing as it ages. Deep inside its core, hydrogen is steadily converting into helium, and over enormous stretches of time, that slowly makes the sun more luminous. That's not a change you'd ever notice tomorrow, or even in a million years. But over hundreds of millions of years, the difference becomes enormous. Earth is currently sitting inside what scientists call a long-lived habitable window. But habitability isn't permanent, and as the sun brightens, that window will eventually close. Earth's surface could eventually become too hot to sustain oceans in anything like their current form, losing the very conditions that made them possible. Long before the sun reaches the true end of its life, Earth's surface may already have become hostile to complex life entirely. And then, in roughly 5 billion years, the sun will exhaust its core hydrogen entirely and expand dramatically into a red giant. Mercury and Venus are expected to be engulfed completely. Earth's own fate is less certain. It may be engulfed too, or survive as an altered world. Either way, the Earth we actually know, the blue planet, with its oceans and its life, will be long gone by then. The planet doesn't belong to us. We're one species, living during one moment, on one planet, orbiting one ordinary star, inside one ordinary galaxy. And yet, for right now, this is our home. And there's nowhere else quite like it that we currently know of. Not yet, anyway. Every morning, the same star rises above you. It's easy to forget what you're actually looking at, a gigantic sphere of plasma, releasing enormous energy. Almost every ecosystem on Earth ultimately depends on that energy. Your food, your body's own energy, the weather, even the fossil fuels that powered civilization. And yet the sun isn't permanent. It was born roughly 4.6 billion years ago, and right now, it's roughly halfway through its entire lifetime. Deep inside, hydrogen nuclei are constantly fusing into helium, and the core is gradually becoming richer in helium. Eventually, that balance will shift. The sun's overall brightness increases across its entire lifetime, meaning Earth receives more energy over time. A slow change that becomes critical over hundreds of millions of years. Eventually, after roughly another 5 billion years, the sun will no longer sustain its current hydrogen-burning phase, entering the most dramatic stage of its life. The red giant phase. Imagine the sun as it is today, now make it larger and larger, eventually swelling to hundreds of times its current size. Mercury will be engulfed completely. Venus will be engulfed too. Earth's fate remains uncertain. It might survive outside the sun's new, expanded surface, or it might not. But surviving physically wouldn't mean surviving as the blue planet we know. By that point, Earth will have already lost every condition required for life. The red giant phase doesn't last forever, though. Eventually, the sun becomes unstable enough to shed its own outer layers entirely into space. For a brief period on cosmic timescales, that dying star creates one of the most beautiful structures in the entire universe, a planetary nebula. At the very center of that expanding nebula, something remains. The sun's exposed core, a white dwarf, compressed into something the size of Earth. It no longer generates energy through fusion at all. It simply stays extremely hot and slowly cools for the rest of time. Think about what this star once created. Energy for billions of years, powering photosynthesis, supporting ecosystems, and making our entire world habitable in the first place. And eventually, the star that gave us all of that will become nothing more than a cold, fading remnant, drifting quietly through space. The sun feels permanent only because a human lifetime is so short beside it. Stars are born, they evolve, and eventually every one of them dies. One day there will be no human left standing here to watch it happen. But right now, the sun is shining, Earth is alive, and you are here. Now zoom out to the true end of this entire story. Eventually, the universe stops making new stars altogether. It simply runs out of the right conditions. One by one, every remaining star burns through its fuel. White dwarfs, neutron stars, and black holes are what's left, scattered through an increasingly empty universe. Distant galaxies keep drifting apart as the universe keeps expanding. Eventually, many will become so far apart, they can no longer even see one another. Even black holes aren't forever. Through a slow quantum process called Hawking radiation, they gradually leak away. Over timescales far longer than the universe has existed. What's left, eventually, is something called heat death. A universe so evenly spread out that no meaningful energy difference remains anywhere ever again. But that's not where this story should end. Instead of asking how everything ends, ask instead, how did any of it actually begin? Inside one ordinary galaxy, around one ordinary star, on one small planet, life appeared. And then it evolved, surviving ocean after ocean, extinction after extinction. One branch became mammals. One branch became primates. One branch became human. Humans learned, remembered, built, imagined, and eventually, one of them became you. The hydrogen in your body traces back to the universe's very first moments. The carbon in your cells was forged inside stars that died long before Earth existed. The calcium in your bones, and the iron in your blood, carry that exact same cosmic history. None of it invented for you, all of it inherited. The universe made stars. Stars made the elements. Those elements became a planet. That planet grew oceans. Those oceans grew life. And life eventually became you. You found out you were never separate from any of it. You're made of the stars, the atoms, and the 14 billion years behind you. So the next time you look up at the night sky, you're not looking at something distant. You're looking at home. You are the story. And it's still being written. I'll see you in the next chapter.